Hi, my name is John Krochmalny, and I've developed these video presentations to orient PLC learners to automatic technology now being used in industrial, commercial, and residential applications. In this presentation, we'll be exploring the components of a typical programmable logic controller, as well as their function in process control. There are three learning outcomes related to this presentation. Number one, describe human aspects to work performance. Number two, describe automatic aspects to work performance. And then number three, name and describe the components of an automatic system and programmable logic controllers. Referencing automatic systems, the term logic is often used. By definition, logic is the science of how to evaluate arguments and reasoning. In reference to the logic involving automation, there are two principles of logic. Number one, two-state logic, and number two, analog logic. Let's look at two-state logic first. Two-state logic has two and only two possibilities and conditions. Things, devices, and conditions are either on or off, working or not working, normal or they're in an alarm, 0 or 1, okay or not okay. Notice that the two-state logic has no other condition being applicable. When given a question in the form of a two-state logic condition, the answer is either yes or no. In electrical devices, examples of two-state condition devices could include switches, contactors, thermostats, motors, and lamps. Notice that all of these devices really have only two working conditions. They are either conducting electricity or they're not. They are either on or they're off. Analog is the other principle of logic applications and includes the actual value of things, conditions, and applications. Analog logic is concerned with how much a position is achieved. Is it 100% open, 50% open, or is it closed entirely? Analog logic relates to temperature, will always give a specific temperature, pressure, and perhaps motor speed. Conditions of 72 degrees Fahrenheit at 100 pounds per square inch gauge and at 60 Hertz are all aspects of analog logic providing actual condition value. Perhaps another way to compare two-state and analog logic is to consider any type of reality and how questions on that reality are answered. Do you have it is a two-state logic question, and how much do you have involves the analog logic. Humans use the principle of logic all of the time in order to solve challenges. The human brain is the location of the stored memory of what is desired. Human body sensors like eyes, ears, touch, and taste sample the external environment of the body. The brain decides what may be needed to correct their environment and will command muscle tissue to affect that change in the environment. Notice the pathway of the decision-making process, from the sensors to the brain and then to the muscles. For humans, before any decisions and related work is to be performed, energy and power are needed. For humans, this energy and power is the chemical energy associated with the food that we eat. Without this energy, we would have no power to do work. The body metabolizes the chemical energy and turns it into usable energy for the rest of the body parts. Some of this energy is also supplied to the human brain, enabling the brain to perform its functions. Once supplied with energy, the brain receives reports from other body sensors regarding present condition. Notice that the body sensors are providing information to the brain in both two-state and analog logic. This diagram sums up how the humans perform work tasks requiring his intervention. If systems are to be operated automatically and without human intervention, they would also have to have the same types of components. Further studying this graphic, we can also consider breaking down brain tasks to the power needed to operate the decision-making process, the necessary inputs to the brain for it to make decisions, and outputs that would be used to take commands from the brain in order to affect condition changes. All modern programmable logic controllers will have these components and are all necessary for the programmable logic controller functions. Programmable logic controllers come in all sizes and levels of complexity, but realize they all have common components. All PLCs have power supplies, processors, inputs, and outputs. Humans need the energy provided by the food they eat to provide that energy and result in power. PLCs have power supplies that do the same. The PLC power supply will have diagnostic LED indicators providing information on the programmable logic controller power supply status. Alternating current and voltage AC to alternating current and voltage AC. Power supplies convert alternating current and voltage to direct current and voltage. In this example, the power supply converts 120 volts AC to 20 volts DC. In this example, the Allen Bradley SLIC 500 power supply is wired for 120 volts AC. The SLIC 500 power supply steps this voltage and current down to 20 volts DC. Notice the diagnostic LEDs located at the top right corner of the power supply. The artificial intelligence of the programmable logic controller is housed in the PLC processor, commonly referred to as the CPU, or Central Processing Unit. If the human brain needs energy to function, the processor also needs energy. This electrical energy comes from the power supply in the form of a 20 volts DC. This 20 volts DC is required if any decision-making processes are going to happen within the brain. The Allen Bradley Compact Logix processor is shown in the graphic. All PLC components will have diagnostic LEDs that provide information on their status. In the case of this processor, diagnostic LEDs indicate 6 conditions related to the processor. The sensors to the processor are called inputs and provide information concerning the outside the brain condition. The input section of the PLC serves as the PLC device that receives information on the external environment or condition. Notice that the PLC input section also takes some of the energy provided by the PLC power supply. In this graphic, the Allen Bradley MicroLogix PLC is shown. This PLC is considered a brick controller and having all of its components existing in one assembly. In the MicroLogix PLC, the input section is located at the top screw terminals of the PLC. Notice that the input screw terminals are identified with an I before the screw number. The I stands for inputs. As you may remember, the human outputs are the muscles that perform the work. In the case of PLCs, the outputs will be doing the desired work determined by the PLC processor. The PLC output section is also provided with its power from the PLC power supply and is in the form of 20 volts DC. The output screw terminals is located at the bottom of the Omron Zen PLC. Notice that the letter Q is labeled before the screw numbers, indicating output screws. The Allen Bradley PLC have their output screw terminals identified with the letter O for output. For any form of artificial intelligence to do work, they all have to have common components needed to evaluate the conditions, determine what is needed to be done to control those conditions, and activate devices to bring those conditions back into desired condition. Programmable logic controllers have technology contained in their assembly to accomplish these tasks. As previously mentioned, PLCs come in a variety of sizes and complexities. The common things about all programmable logic controllers are that they all have power supplies to provide assembly power, processes to provide the intelligence of the system, inputs to gather the conditional information, and outputs to control devices serving that condition.